welcome to this IChemE Global Awards webinar. My name is Matt Stalker and I'm your host for today's presentation. The IChemE Global Awards celebrates chemical, process and biochemical engineering excellence and are widely recognised as the world's most prestigious chemical engineering awards. Today we'll be announcing the winner of the IChemE 2020 Sustainability Award, sponsored by Johnson Matthey. This award recognises the project, process or product to best demonstrate excellence in sourcing, waste reduction, recycling, reuse, or the lengthening of product life cycles. And joining us now is Johnson Matthey's Projects and Engineering Director, Ashley Anderson.
Good morning. Can everybody see me? Am I in full view? Yep. Okay. Just give me a second on the. Yep. Right. Okay. Sorry, I'm just got some barriers there. Right, fine. Right, hello and good morning. Ashley Anderson here. As Matt said, I'm Director of Projects and Engineering at Johnson Matthey, and a very warm welcome to all the finalists in the Sustainability Award. It's a pity we can't be all together in Manchester, but I'm sure with the good news and promising news of the last week or two that there's a possibility next year we might be able to get together, and that's it's always a great event. I was actually thinking of putting on a bow tie and a DJ today, but I thought that was a bit much for a Wednesday morning. So anyway, I'd just like to talk a bit today about Johnson Matthey, sustainability and climate change. Probably only take about five or 6 minutes, but I'll start on Johnson Matthey. So it's great pride that Johnson Matthey presents the IChemE Award for Sustainability, as it's one of our core embedded values, protecting people and the planet. The world is facing a very set of a set of complex challenges: climate change, the need for clean air, and the drive for improved health. And there's responsibility to be smarter and more efficient in the way that we use the world's finite resources, natural resources. So in setting our vision for a cleaner, healthier world, we've made it our business to create sustainable technologies that address the challenges being driven by global megatrends. And in fact, sustainability is an integral part of our company, our strategy, and the decisions we take. As JM is a leader in sustainable technologies, we apply our expertise in science and engineering to develop the solutions that create value for our customers and have an impact globally, leading to making the world cleaner and healthier today and for future generations. We deliver that through 4 global sectors: clean air, efficient natural resources, health, and new markets. So just to give you some examples, in clean air, we're a global leader in catalyst and catalyst systems to reduce emissions from vehicles and industry, serving the automotive and energy markets. In efficient natural resources, our products and processes transform, conserve, and recycle scarce resources, using less energy and fewer raw materials across the chemicals, energy, automotive, and pharmaceutical markets. And in new markets, we apply our science in emerging opportunities, such as battery materials, fuel cells, and enabling the shift occurring in the automotive, chemical, and energy markets. So there's an immediate need to address climate change, and the expansion of the hydrogen market. JM has an important role to play and significant expertise in enabling the transition to the hydrogen economy. And there was some news about that, which I'll come on to at the end of the news of that out today from the government, but I'll come on to that at the end of the session. Hydrogen is essential to the UK meeting its net zero emissions target, and we must act now to scale hydrogen solutions and achieve cost-effective decarbonisation. JM's technologies are already at the heart of enabling the transition to a hydrogen economy. Our market-leading low-carbon hydrogen technology has been selected for groundbreaking new clean hydrogen projects in the UK, and our fuel cells technology is already out on the roads powering more than 700 zero-carbon buses. We're also applying our core science capabilities and market expertise to drive large-scale adoption of green hydrogen. Now, I thought then, just as it's a sustainability award, I'd just talk a little bit more about the wider aspects of sustainability and climate change. Sustainability is often talked about, and many people might take different things from it, but essentially there's three main pillars of sustainability. That's environmental, economic, and social. And they're all interdependent. In 2015, the United Nations established 17 Sustainable Development Goals, which essentially are the blueprint to achieve a better and more sustainable future for everyone on the planet. They address global challenges faced and include. They address the global challenges faced, including poverty, inequality, climate change. Hello, I'm getting a bit of feedback.
Yes, so are we. I'm trying to work out what's going on. If anybody can mute their microphone, please.
Please make sure you take all your personal belongings with you.
I'll just hold until the tech is. That seems to be okay. Yep. Yeah. If everyone could just mute their headsets, please, that would be great. So yeah, the 17 Sustainable Development Goals. They address the global challenges faced by the planet, and they include poverty, inequality, climate change, environmental degradation, peace and justice. So they are quite wide-ranging, and as I said, they're sort of all interconnected. And Johnson Matthey's orientated its own goals with these UN Sustainability Development Goals. Turning specifically to climate change, the landmark report by the United Nations Intergovernmental Panel on Climate Change paints quite an alarming vision of the future if we collectively don't endeavour to decarbonise our economic systems and stabilise the level of greenhouse gases in the Earth's atmosphere. Consequences of inaction include threatened ecosystems and biodiversity, water and food scarcity, rising sea levels, increased ocean temperature and acidity. This report, and it was compiled by hundreds of scientists over a number of years. The report considers pathways for atmospheric CO2 reduction to limit the global average temperature rise to 1.5 degrees centigrade, with the endeavours of trying to reach net zero around 2050. It's worth noting that delaying that net zero to 2070 would lead to a 2-degree temperature rise. And in that report, that gives you various scenarios depending on the level of temperature rise. I would really encourage everyone to try and get an overview of that report. And there's quite a good summary version produced, which only should take about half an hour to read. So that's the summary IPCC report on global warming. I think as it's a chemical engineering award, the chemical engineering community has a unique ability to understand whole systems, and it will be front and center in the drive for sustainable life on the planet. And examples of sustainability innovation in our industry are really showcased by the excellent finalists in this award category. I have to say, I always like looking at the the award summaries, because throughout the 20 or so awards and these events, there's some absolutely excellent projects, excellent innovation, excellent categories. And as engineers and scientists, I believe we all have an important responsibility to take the time to understand the impacts of global warming and that pathway to net zero, and then also to try and help explain the immediate need to address climate change to the wider population. It's not really something we can put off and start in a year or two. It does need to start now, and it's particularly fitting that today, complete coincidence, the UK Prime Minister has they just released a press release about an hour or two ago about an ambitious 10-point plan for the green industrial revolution. I think they're going to put in about 12 billion funding to get it going, and they're looking to create up to 250,000 British jobs, particularly important at this moment in time. And this plan covers clean energy, transport, nature and innovative technologies, allowing the UK this is from the press statement, actually, I just pulled it off this morning, allowing the UK to forge ahead with eradicating its contribution to climate change by 2050, and particularly crucial in the run-up to the COP26 climate summit in Glasgow next year. So, so that's a sort of around you know, around Robin on Johnson Matthey, sustainability and climate change. But I do urge you to read the IPCC climate report. So as we proceed with the IChemE Sustainability Award ceremony, I wish all the finalists the best of luck in a very strong category. And with that, I'll hand you back to Matt.
Thank you very much, Ashley. And a big thank you to Johnson Matthey for its sponsorship. Ashley will be back with us later to announce our award winner. Before we check out the finalists, just to let you know, we're live tweeting throughout all of our 2020 awards webinars. You can also get involved using the hashtag IChemE Awards. So without further ado, here are our finalists. We start with Dow Europe. We have a joint entry from Dow Europe and H&S Anlagen Technik. A joint entry from Green Lizard Technologies, Abundia Plastics, Kerax, Petronas Lubricants International, the Netherlands Process Design Centre, River Ridge and Yashantech. Impact Recycling, Petronas Penipizan, winner of the IChemE Malaysia 2020 Sustainability Award. Plastic Energy, Sunwind Solutions Malaysia, winner of the IChemE Malaysia 2020 Palm Oil Award. And finally, a joint entry from University College London and Heathrow Airport. All our finalists have been invited to join us today to give a short presentation on their work, and subject to time, we'll be inviting you to participate in Q&A at the end of each presentation. You can ask your questions via the questions box on the GoToWebinar portal. With that in mind, please welcome our first speaker from Dow Europe. It's Karl-Heinz Hausmann.
Yeah, good morning, everybody. My name is Karl-Heinz Hausmann, and I'm working for Dow Europe. I'm Senior TS&D R&D Fellow in Horgen, Switzerland. I hope you see my screen.
Yes, we do.
That is fantastic. So I'm going to talk about a polymer development addressing sustainability aspects, so oriented polyethylene for recyclable flexible packaging. As you know, and now I'm trying to advance the screen. Yeah, as you know, plastics are perceived negatively in the society, and we are producing plastics at Dow, and this requires a need for collection and recyclability of plastics. We have therefore developed a circularity strategy that addresses this issue, and this consists of 4 pillars: design for recyclability, mechanical recycling and product development, feedstock recycling solutions, and bio-based alternatives. And within this talk or submission, I will talk about design for recyclability. So this is called focusing on design for recyclability. Then we have asked ourselves, what is recyclability? And this is very easy to answer. A package is recyclable if it is collected, if it is sortable and eventually sorted, if it can be used in products for which a market exists. So there must be a market that requests this product, and if the above is happening on scale. This can, of course, depend on the region and on the readiness of the region. And we are active in different organizations to help develop guidelines to actually make this happen. For example, we are member of Recyclas, CFlex, and also have been member of the Ellen MacArthur Foundation. Now, in order to make this happen, to redesign packaging for recyclability, we have developed an entire collection of different technologies with which we help our customers and with we help our brand owners in a kind of value chain collaboration to redesign packages for recyclability. And one of these is orientation technology, where we are actually developing products that allow to make polyethylene thinner and stronger, so to use less material but to have a better protection of the packaged good. One of these is a whole collection or a whole portfolio of polymers for the orientation, biaxial orientation process. These kind of thin films, they usually have different layers, but these are mono-material multi-layers. And we have developed a portfolio consisting of an LLDPE, of an HDPE, and of a sealant material. Now, how does this process work to make thin, strong polyethylene films? First of all, you have a cast sheet extrusion, then you orient this film in a machine direction, then you orient it in a transverse direction, so it's a sequential process. Typically here the orientation ratio is 5, and here the orientation ratio is 9. So overall you have a 5x9 orientation. That means if you start with a film that is 700 micrometers thick, you end up with one which is about 20 micrometers thin. So orientation ratio of about 40. The final film is 40 times thinner than the initial films. And you can imagine this is a very stringent process. I wouldn't support it. I would die after this one. Many of the polyethylene films or polyethylene polymers also will crack or die. So in order to overcome that, we have developed a new polymer system or new polymer type, which has a special molecular architecture, which provides a stable orientation in industrial scales, existing BOPP lines, oriented polypropylene lines that are already in the market. One LLDPE types 1.7 MFI and a density of 0.926. The other one is an HDPE with a density of 0.967. And this polymer provides films with excellent toughness and optical properties, very good stiffness, and lower temperature resistance, so you have a very tough material. The idea here is to use this polymer films based on this polymer in a multi-layer but monomaterial film and replace existing multi-material multi-layer films that contain polypropylene or polyester or polyamide together with polyethylene that are very difficult to recycle. And this resulting film is very easy to recycle because it's one material, it's polyethylene. So it's recyclable, has excellent optics, very good clarity, easy tear, and is also down gaugeable. And we can use that for printing substrates or for sealable film substrates. 3 case studies. One is the all PE pillow pouch. Typical applications: detergent powder, frozen foods, snack foods, and so on. This is how it looks like, the blue one here. And the approach is to replace a multi-material multi-layer structure with a monomaterial multi-layer structure, replacing polyamide with polyethylene. You see, the performance is quite similar. There are slight performance differences in tensile strength and elongation, but still this gives a very good opportunity, a very good alternative to non-recyclable multi-material multi-layer structures. Second example, all PE, all polyethylene standard pouches for dry foods and liquids. You see that here in the background of the picture. Again, the approach is to replace these multi-layer structures based on multi-materials with monomaterial multi-layer structures. And the result is actually quite surprising. We have a very flex crack resistant polymer. So after 13,000, we stopped the test because afterwards we still could have continued. It's much better than comparable material. Very good glossiness, very good impact resistance, very good drop resistance, which is important for this standard pouches. Now, third example, a down-gauged label film, which compares or which combines clarity with good conformability in the printing machine for the labels, very good haze. So we have very low haze values here, very transparent film. We have reasonable stiffness with this film, and that also is basically replacing multi-material films or blown films in this case. So in summary, the oriented tenterframe BOPE type of polymer film shows basically that plastics and plastic packaging is recyclable, no? And can replace PET, polyamide, polypropylene flexible film applications. And we have here developed an entire portfolio of orientable PE types, so not only a high HDPE or LLDPE film, but also a whole sealant film and so on. This fits very well in our sustainability strategy that we have developed in Dow, which also comprises, for example, chemical recycling and bio-based materials. Thank you very much for the opportunity of presenting this solution.
Okay, thank you, Karl-Heinz. So we will now pause for questions. If you have a question about our first presentation, please type it into the questions box on GoToWebinar. Well, I'll give you a moment on that. Now is a good time to thank our volunteer judging panel, led by our head judge, Keith Batchelor. The judges have worked tirelessly to review and score every entry across all of our categories. You can find out more about the judging panel on the IChemE Global Awards web pages, icheme.org/global awards. Okay, we don't appear to have any questions, so thank you very much. We're going to move on. And it's time to welcome our next speaker, representing the joint entry from Dow Europe and H&S Anlagentechnik. It's Lucy Porcelli.
Hello, everybody. Can you please let me know if you see my screen?
Yes, we can see your screen.
Perfect. And I hope you can also see the presentation right now.
Yes, we can.
Perfect. Thanks a lot again. So hello, everybody. It's a great pleasure to be here with you today. My name is Lucy Porcelli, and I'm representing Dow Europe and H&S Anlagentechnik for this entry for the Renuva mattress recycling program. Before I go into and explain the program and the key benefits of it, I would like to mention that at Dow, as Karl-Heinz just presented, we also see for polyurethanes the place as they will be clearly enabling the low carbon and circular economy for the future. Now, we need to still work and to fully unlock their sustainability potential by addressing sustainability along the whole polyurethane life cycle. And today we will be talking about the end of that life cycle, really questioning how we can give value for the waste materials, polyurethanes, even though they are kept at use for a long time, somewhere between 10 to 50 years most of the time. If we look for the future, we have to make sure that even after 10 or 50 years, these materials can be recycled or reused. And this is exactly the point Renuva is demonstrating. You will see throughout the presentation that we will address 3 key points of Renuva. Number 1, it is addressing the waste issue. Number 2, it is a demonstration that polyurethanes are recyclable. And third, it highlights the need for collaborations as we move towards the circular economy. So let's start with that waste. I would like you to think about last time you bought the new mattress and actually think about what happened with your old mattress. Because today, only in Europe, more than 30 million mattresses are wasted every year. If we were to stack those mattresses up, the height of the pile would be 678 times higher than the Mount Everest. The sad news is, majority of this waste is ending up in landfill or incineration, and polyurethanes are more than a third of all those materials. So the question is obvious: how can we make sure that the waste can be valorized? And here Renuva comes. We are really creating a new circular economy roadmap, which wants to recycle the end-of-life polyurethanes products in collaboration with the value chain. And you see on the circle that this cannot be done in isolation. And for us to work to really address the waste issue, we need every single part of this value chain to work together. Like this, we will be able to have the larger impact because we will be able to reuse or recycle more waste. We can leverage expertise, create new jobs, encourage innovations, and really enhance further collaboration. Second, and probably one of the most important things as a demonstration, is the fact that Renuva is clearly showing polyurethanes are recyclable. It's great to be presenting just after Karl-Heinz, because he just mentioned what does it take for polyurethanes to be recyclable or for materials to be recyclable. And this is a demonstration that polyurethanes, even though they are believed, they are thermosets, hard to recycle, it does not need to be true. Renova is here to demonstrate that polyurethanes recycling at industrial scale is possible. We are using chemical recycling of polyurethanes, which really change the structure of the substance back into raw materials, which can then be used to create new products. When we talk about polyurethanes and flexible foam especially, this is important because this chemical recycling really eliminates a need for further cleaning and sorting of the polyurethane waste in the beginning. We also see that the polyol, which will be recovered out of that polyurethane foam, can be used for a variety of applications, and there will be no downcycling. The quality of that material stays the same, so the final article can be produced with the same amount of quality. We don't need to segregate different polyurethane flexible foam, and important as well is that we have immediate impact on the balance. I said it in the beginning, we have a huge waste issue today. We are burning all the value which can be reused or recycled. Even if the industry today starts designing mattresses which are ready to recycle in 10 or 15 or 20 years, it will take a long time. And before we get there, every year there will be more than 30 million mattresses wasted. So we have to act now. And that's where the benefit of Renova is. It can recycle the mattresses which have been produced a long time ago. And last but not least, collaboration. If we want to move to circular economy, collaboration along the whole value chain will be more critical than ever. And in circular economy, collaboration really starts from the waste. In the Renova program, which is currently being implemented in France, we have a great partner in Ecomobilier, who is the extended producer responsibility scheme for furniture and mattresses in France. And they will be supplying the polyurethane foam from the end-of-life mattresses to the process. We also have HNS Anlagentechnik here, who is the German engineering company specialized in the polyurethane industry, who provides the process know-how and turnkey installations to the Orion Chemical Orgafoam, where the first installation will be implemented. Orion is the external producer for Dow and will operate the plant on Dow's behalf. Dow will then make sure that we supply all the materials, of course, but then also that the resulting raw material, which is for the first time polyol with recycled content, approximately 50% recycled content, is first compliant to all the regulations, and second, fit for applications, and there is enough market for those kind of polyols. And as I mentioned, if we want to move to circular economy, we also have to make sure that market creation and that the demand can be taken care about since the beginning. And that's why we also have the Vita Group, part of the Renova program, so that they can take the polyol with the recycled content and create the new flexible foam with this material. To summarize, we really see Renova having impact on society, environment, and of course also the economy. It is addressing the waste issue. For mattresses now made with polyurethane foam, there will be no need for landfill or incineration. Polyurethane, the Renova program is a demonstration that polyurethanes can be recycled, and doing so in the environmental friendly way, because according to the preliminary LCA, will be roughly saving 30% of CO2 emissions versus the conventional polyol. And last but not least, collaborations are critical when we move towards circular economies. And we can also, by doing so, we can also empower you, the consumer, every one of us. Next time we go to buy a new mattress, to buy the new mattress produced with some recycled content. Thanks a lot for your attention, and I'm very happy to take any questions.
Okay, thank you very much. So once again, we pause for questions. If you have a question, please type it into the questions box on the GoToWebinar portal. Our first question has come in. There is a lot of development of polymer production from biological sources. Can you comment on the materials you produce with compatibility with these manufacturing methods and their recovery?
Look, I think this is exactly the great point. And I started the presentation with the fact that we have to address sustainability along the whole life cycle. And looking at the raw materials we are using for polyurethanes is clearly also an important part. When we talk about renewable, what we wanted to say is that we need to also address the waste issue. So yes, using bio or recycled materials to start the new polyurethane material is very important. But it does not solve the waste issue. Even if we produce bio polyurethanes, we still have to make sure what happens with those products at the end of the life. And that's exactly where the renewal comes in play.
Okay, thank you. There are no more questions, so we'll move on. Thank you very much for that presentation. It's now time for our third finalist, representing the joint entry from Green Lizard Technologies, Abundia Plastics, Kerax, Petronas Lubricants International, the Netherlands Process Design Centre, River Ridge and Yashantech. It's Mark McCoy and Martin Atkins. Mark, we just need you to unmute your microphone.
Sorry about that. I hope you can all hear me now correctly.
Yeah, that's fine.
And see my presentation?
Yes.
Okay, so today I'm going to be, so my name is Mark McCoy and I work for Green Lizard Technologies. I'm a chemical engineer and I've been working on one of the recent projects here, which is the pyrolysis of waste plastic. So I'm going to talk you through, first of all, the problem and the opportunity. So we're trying to assist the UK to reach their plastic pack targets, which by 2025, 100% of the plastic packaging will be either reusable, recyclable, or compostable. There are many different types of plastic. We will be dealing with polyolefins. So where exactly or what exactly are polyolefins consist of? Well, polypropylene and polyethylene are the main components of polyolefins, and they either are in the form of low density or high density. They are mainly used in plastic packaging, film packaging, electrical insulation, or in containers. These can be found mainly in MSW streams. They're mainly found in MSW streams because they cannot be recycled conventionally using mechanical recycling techniques. And so we're going to tackle recycling these polyolefin plastic compounds by using pyrolysis. And pyrolysis is the thermal breakdown in the absence of oxygen, breakdown of long chain plastic polymers into shorter, smaller chain polymers. And you form a spectrum of these products, which are similar to the products that are presented in crude oil. And these spectrum include light products such as fuel gas, naphtha, and then heavier products like diesel, and then heavier ones like lubricants and waxes. Once we form these products in pyrolysis, we will then be sending them to our partners in Yashantech for hydrogenation. This is a refining step which will help bring the products to market. So what is our value chain? So we plan to build the first plant in Northern Ireland, in Coleraine, with our partners River Ridge. They are the waste management company who will provide us with the plastic-rich feedstock we will be using. So when the plastic-rich feedstock enters our pyrolysis unit, we will be processing three main streams: light gases, heavy naphtha, and crude waxes. And these will then be sent to our downstream customers for upgrading and bringing the products to market. It is very beneficial having these large reputable companies in with us, working with us to help bring our process, our technology to commercialization. So what actually makes us different, and where is our know-how? Well, our technology has the ability to handle a dirty plastic waste, and this benefits us as the pre-treatment of the waste is very much limited. We don't need as extensive pre-treatment as other technologies, and so with that we have a lower energy cost and therefore more attractive economics and less environmental emissions respect with this. So this technology simultaneously removes plastic from the environment whilst also displacing fossil fuel derived chemicals from the economy. Pyrolysis produces a spectrum of chemicals under all conditions, whether it be low temperatures or high temperatures. And we're going to be focusing our attention to waxes, which are produced on low temperatures. And they're going to be our primary product, as they have the highest value whilst the lowest environmental effect. And these will be go on to use in coatings, lubricants, and specialty waxes. So our market and our customer base, well, our upstream customers will include waste management companies such as I previously mentioned, Riveridge, or others such as Biffa or Veolia, and they'll be able to provide us with a plastic-rich feedstock. Our downstream market, mainly for waxes, is quite a big market, $5.6 billion in 2019, and is set to grow at a rate of 3.8% to $7.71 billion in 2027. And this demand is mainly in the cosmetic industry, as there's huge demand. Our other downstream partners include SHV Energy, Color Gas, Ineos, Crown Oil, Petronas, Kerax, and also Yash and Tech, who will be helping us with the hydrogenation section. So our technology and our competition, there's quite a drive for this pyrolysis technology in recent years, although the technology's been around for some time. And with this, there's a lot of patent and IP information, and we'll be developing our own patent and IP based on our unique process. And we believe that our business model and technology will give us a greater advantage over our competitors for various reasons. So what are our next steps then with this technology? So we'll be processing a known feedstock from Riveridge through our partner's pyrolysis facility, and these products or these samples will then be sent for hydrogenation and then to our downstream partners and customers to verify the quality. Our research and experience then will be used to develop a large commercial plant for the Coleraine facility at Riveridge. And with this, we'll be securing our commercial partnership agreements with these larger companies upstream and downstream. We'll be continuing the market research, identifying competitors and any developments with this pyrolysis technology, and we hope that this will be a good process for the future for tackling these non-recyclable plastics and helping clean up the environment. So thank you very much for listening, and if you have any questions, please feel free to ask.
Okay, thank you, Mark. So once again, we pause for questions. If you have a question, please type it into the questions box. We have our first question. What is the economic scale of production? Sometimes smaller local units are better than large centralized ones, as it avoids large transport distances.
Sorry, the internet connection broke up a wee bit there. Could you repeat the question?
What is the economic scale of production? Sometimes smaller local units are better than large centralized ones, as this avoids large transport distances, which negatively affect the environmental benefits.
Well, we're actually considering having several pyrolysis units in series, and the benefit that this gives us is, depending on the oil prices, we can adjust the temperature of pyrolysis to maximize the production of a specific product. And if we have several products that are wanting to maximize in production, then we can adjust the temperature of one train to maximize, say, waxes, and another train to maximize, say, LPG gases. So we can sort of manipulate the process conditions to benefit one product, and then with this we can transport that product out in various loads. So I hope that sort of answers your question, having a couple of different trains there instead of one big unit to handle the whole system.
Okay, thank you very much. We have no further questions, so we'll move on. Thank you for your presentation. Our next finalist is Petronas Panipizan, who have submitted a video showcasing their work. Let's take a look.
Hello everyone, my name is Muhammad Fazli from Petronas Penapisan Terengganu Sdn Bhd. I will be presenting on Steam System Closed Loop Real-Time Optimizer implementation in our company. First, let me introduce a bit about our company. Petronas Penapisan Terengganu Sdn Bhd, which commonly known as Kerteh Refinery, is a wholly owned subsidiary of Petronas. It was incorporated in March 1982. On top of being a refinery, we also function as managing operator of Petronas Chemical Aromatics Sdn Bhd, or known as PC Aromatic, which was incorporated in year 2000. Our current business model is processing arrangement with Petronas Trading Corporation, PETCO, which means that we are being paid for amount of feedstock being processed. And some overview on the size of our manpower. Our company consists of 482 employees. Moving to the Steam System Real-Time Optimizer background, the project is one of crucial initiatives in supporting our company's strategic direction to achieve world-class operational performance. This initiative supporting our HSSE and OE initiatives, which contributes to environmental sustainability program and energy improvement program. For your information, the initiative is driven by three main critical issues, which are high energy index, EI, rising of fuel gas costs, and disconnected optimization. Let's look into some details of the three critical issues. The first one is high energy index. Our refinery energy index for 2019 recorded 4% higher than target. Higher energy index means high usage of energy, which also contributes to high greenhouse gas emission to environment. The second issue is rising of fuel gas costs. We are facing fuel gas cost increment every 3 to 6 months, which contributes to increase of operating costs. The diagram gives you some view on our fuel gas cost increment from 2016 to 2019. The final issue is disconnected optimization. There are a few existing optimization efforts in our Steam system, but they are independent and not linked to each other. This becomes a barrier for us to achieve overall benefit from the optimization. Next, I will share on how Steam System Real-Time Optimizer can address the issue mentioned earlier. For the implementation, we plan to have items as stated below to be incorporated in the initiative. We want to expand the optimization boundary to the whole Steam system instead of focusing on a few equipment. And we want to integrate multiple optimization initiatives in the Steam system and ensure they are aligned to each other. Next, we want to have closed-loop real-time optimization with our existing Advanced Process Control (APC), which allow us to directly conduct process adjustment based on optimization target. And lastly, we want to have supervisory optimization recommendation for our panel operator. As mentioned before, the Steam System Real-Time Optimizer expand optimization from Steam producer boundary to bigger boundary of Steam system. We are moving from this to this. These are our design objectives. The optimizer were designed to do real-time first principle process estimation and identify optimization point for steam system, to regulate boiler steam production in closed loop with APC controller, and to provide recommendation for turbine to motor switching in open loop supervisory. Some overview on the optimizer system. Process data from control system and historian system are fed into optimizer. The system will then calculate and decide on optimization target based on current process condition. The optimization target was sent to two destinations, supervisory target to DCS and closed loop target to APC controller. Closed loop optimization target to APC will automatically executed by APC controller in each control cycle. This also ensures continuous optimization action take place. Supervisory optimization target was sent to control panel for panel operator reference and action. Panel operator can also provide inputs of equipment maintenance for optimizer system to use in calculating optimization target. While some optimization normally have fixed optimization target, Steam System Real-Time Optimizer can have multiple targets based on actual process condition. This is the improvement made by the initiative. We recorded reduction of about 58,000 gigajoule from fuel gas consumption in steam generation within 9 months period. This is equivalent to cost saving of 1.94 million ringgit. Our steam production also recorded reduction in year 2020 as Steam System Real-Time Optimizer as one of main contributors. And the most important thing, Our effort in reducing fuel gas consumption also meant to reduce greenhouse gas emission to the environment. We recorded about 2% of GHG emission reduction from combustion process in year-to-date Q3 of year 2020. And with sustenance of the initiative, we will ensure continuous emission reduction in the future. Last but not least, our STEAM system real-time optimizer implementation supports United Nations sustainability goals, whereby we are focusing on responsible consumption and production and climate action goals. With that, I end my presentation. Thank you.
Okay, that was a pre-recorded video from Petronas, so no Q&A on that one. Instead, we'll move on to our next finalist. It's Plastic Energy, and please welcome Carlos Monreal.
Hello, good morning. Do you see my screen?
Yes, we can.
Yes, perfect, very good. Thank you very much. So, good morning, everyone. My name is Carlos Monreal. I'm the CEO of Plastic Energy. This first slide is the representation of one of our existing chemical recycling plants operating. This one in particular since back in 2015. I'm going to be talking about chemical recycling today, and why chemical recycling could be an important element to really be able to increase recycling and improve the way that we manage the plastic waste that we produce. As we notice, we are producing something like about 1 million tons of plastics every day. These quantities are expected to grow over the next coming years, particularly in Asia, because of the demand of the new developing countries, and expecting to have a product that will increase and could improve their quality of living. And however, the plastics, once that we use it, we only recycled less than 14% of the total production, with something more than 40% going to landfilling in the best case, or 14% incineration. This is obviously not a solution, and the conclusion is that there are more than 8 million tons of plastics ending into our oceans every year, and that is something that we have to stop. It's not a question to really collect plastics that are already in the environment, which has to be done too, but critically important is to establish the proper infrastructure to be able to increase collection, sorting, and recycling of those type of plastics. Everything really started to change significantly back in 2017, when China banned the importation of highly contaminated plastics to be recycled into China, where that represented more than 60% of all the global exports of end-of-life plastics globally, and they decided not to continue being the landfill of the world. And that made mainly made Europe, USA, and Japan, Australia, developed countries having to look for alternative places to dispose plastic waste, and that end up going into Southeast Asia with lack of infrastructure to process it, and then really increase it, the awareness of the media trying to look for solutions for what was happening to the waste plastics once that they were exported to these developing countries. So mainly that made trigger policies and the different governments that will start to increase recycling targets all across the globe, and made companies to incorporate commitments to increase recycled content within their packaging in particular. So why chemical recycling in general is a solution? And chemical recycling, there are different type of technologies to address different type of materials, But in general, what we can say about chemical recycling is that today, for the last 20, 30 years, we have been using plastics and sorted those type of plastics by type of polymer, wash it, and later on mechanically recycling those plastics to be able to produce some type of pellets that could be used for certain applications. However, most of the flexible packaging that could represent a big part of the plastics being produced, that is normally taken following the red arrow that you can see in the slide, that normally end up in the northern part of Europe into incineration, or in the south of Europe into landfill, like it happens in the USA or in Southeast Asia. And with the additional challenge or problem that some of those plastics also end up leakage into the environment, particularly in countries that they don't lack or they don't have the proper infrastructure or investments to be able to do the collection. So with chemical recycling, we are really trying to take every type of plastic that is following today the red arrow, to take it into a chemical recycling plant where we could be able to convert those plastics into high value liquids that could be used, in our case of plastic energy, into an output that could be used as a feedstock by the petrochemical companies to replace fossil oil feedstocks when producing new plastics. Who is Plastic Energy? Is the company that has the longer than 10 years experience developing the technology. It's not, we have the technology patented globally and have operational plans. It's not PowerPoint. It's really it's a reality that we have one of them operating since 2015, the second one since 2017, and we are the only single company worldwide that has demonstrated that it's possible to recycle plastics and to produce a liquid to produce new products into a concept that we call plastics to plastics and not plastics to field, which is something that can also be done with chemical recycling. We have strong partnerships. It took us several years to develop great agreements with the most important petrochemical companies globally, as well as with different parties within the value chain. I'm going to present a video. See if I can. Yeah.
Humans have always developed technologies to improve the quality of living. Plastics have enabled us to reach space, have improved agricultural production, and enabled food and water to be distributed in a more hygienic way. They've also revolutionized healthcare and helped to save lives every day. However, our lifestyle also generates serious problems due to the ways in which we use plastics. With a life cycle of less than 12 minutes, the plastics that we use and throw away every day are rarely recycled and end up piling up in landfills or in our oceans and rivers forever. It is estimated that our oceans hold in excess of 150 million tons of plastic, and that almost 70% of the seafood we normally consume has traces of microplastics. If we continue in this direction, by 2050, there'll be more plastic than fish in the sea, and the situation on land will further worsen. How can we manage this plastic wave which threatens our planet's existence?
Plastic Energy has been working to find a solution over the last 10 years. And today, we have good news to share.
Thanks to a unique process, we've been able to recycle the plastics no one wants and which cannot be mechanically recycled to obtain taka oil. It's an oil which can be used to produce new plastics or alternative transport fuel with a low carbon footprint. This technology reduces fossil fuel consumption used to create virgin plastic. This is not science fiction, it's not a project or a dream. It's a reality which is already up and running 24/7, 365 days a year at our plants in Almería and Seville in Spain. It allows people to continue enjoying the advantages of plastic while minimizing its detrimental effect on the environment. This is a new hope for plastic recycling, which we'd like to bring to the entire world, and a process which has made us world leaders in the circular economy of non-mechanically recycled plastic.
It is a great sign of hope that this mechanism has been found, and surely there must be more solutions that the brains of scientists can produce that will help us with this appalling situation.
We've created a new technology which is making a big change. A change which on a daily basis inspires and motivates our employees in London, Almería, Seville, and which will enable us to jointly make a difference in a world where using plastic will no longer be a threat. A technology which will help us look after our cherished planet. Plastic Energy, technology to recycle our future.
Hi. So, do you hear me now?
Yes, we do. Yes.
Yeah, perfect. Thank you very much. And also the slide?
Yes, we can see the slides.
Yes, thank you. So, the mission of Plastic Energy is to really increase recycling and convert difficult or to recycle plastics into high quality liquids that can be used for food grade applications, and by reducing the oil dependency in the current feedstocks used by the petrochemical companies to produce plastics. We have signed the Ellen MacArthur Foundation New Plastic Global Commitments, aiming to process more than 300,000 tons of low-grade plastic waste into feedstock by 2025. The type of feedstocks that we can process is any type of plastics, PET and PVC. You can see here on in the slide the color of the type of plastic that we are processing. We do not have to separate it by type of plastics, but obviously the higher the contamination that we have with the feedstock, the lower the yields and the lower the economics of the process. Is the right size of this type of chemical recycling plant in order to make economical sense. We are talking something in the range of over 15,000–20,000 tons of plastics to be processed per year, and that will have a conversion yield of for every 1 ton of plastic coming into our process, something like about 850 liters of taq oil, which is the brand name of the oil that we produce, that stands for thermal anaerobic conversion oil. This type of taq oil is being sent later on to the cracker and blended with the different with the naphtha feedstock. Looking to how the technology works in a simplistic way, the plastic that we receive, we process it then through a extruder, where we increase the temperature to 250 to 300 degrees, and then it goes directly to the reactor. And that this reactor, we increase the temperature to something like about 450 to 500 degrees. Normally done this with the synthetic gas produced on the process, and in order to make the whole process being energy neutral after the extruder. So that has been a big achievement into this type of technology. The concept is that pyrolysis normally is a highly consumed of energy, but we were able to really manage the synthetic gas in order to be able to use it in the process and make the process energy neutral. Otherwise, you have to use natural gas to heat up the reactor, and that is obviously requires is a lot of energy. So once that the plastics goes through the reactor, it goes later on to the contactor and then to different type of distillation columns where we produce the different cuts that we want for our process, and mainly lately and now 100% in our plants only to produce taq oil to be used as a feedstock for the production of new plastics. Some examples of this closed loop of a solution is was presented in Davos in 2019 with oil produced taq oil from our process and converted into pellets by SABIC, and then sold to different brands like Unilever, Benson, Walkie Group, or Tupperware. Later on in 2020, also with Berry and Mondelez. And the good thing about this process is that it not only works, but really it is we follow the traceability of the process. It's certified by ISCC Plus, and the recycled content follows a mass balance type of approach. Again, the beauty is that the quality produced, it can allows for this type of solution to be used for food grade applications. More examples is recently it was also announced with Unilever with a Magnum ice cream, where the tap is produced out of taq oil, and the North Packaging, and a couple of months ago also made an agreement with Tesco supermarkets, where they are distributing in the Bradbury cheese made with packaging produced from taq oil, processed through SABIC, and with seal air as a converted preparing the packaging. Very important is to address what is the life cycle analysis of this process, and we have conducted an independent analysis by the company Quantis, following the ISO standards, and the conclusions are extraordinarily positive in regards that it has our process at Plastic Energy has a lower climate change impact than incineration with energy recovery, and also lower climate change impact than virgin plastics. So we believe that together, joining forces with mechanical recycling, we could be able to greatly reduce the environmental impact of the plastics once that we have used it. And looking long term, we expect improvements in efficiency on the different process, because we still consume energy within the utilities of the plants that we expect to be able to improve and get better CO2 footprints in the process. We have, besides the 2 plants that we have operational in the south of Spain, we are going to expand the project in Seville. Is starting in Q2 next year, and also another project kickoff will start in Tenerife also by the end of next year, with several projects from in the UK with feedstock supplied by Bidor, or in the Netherlands the first project that will be built together with SABIC, or Total in France, Malaysia with Petronas, or several projects under different phases of development in Southeast Asia and Indonesia. This is the presentation. Any information about the LC8, you can find it in the web page, where we have uploaded the results of the LC8 that I believe it will be very interesting for anyone particularly interested in sustainability. Thank you very much.
Okay, thank you very much, Carlos. Once again, we paused for Q&A, so if you have a question, please send it to us. We have 2 already, and they're interlinked in some way, so I'll ask you them both before getting an answer. The first is, are there issues with contamination for example, fire retardant plastics, and how do you separate them if there is a problem? And the second is, how do you handle plastic in composite materials, or how do you segregate PET, PVC and others in a cost-effective method? Carlos, we can't hear you.
I was in mute, sorry, thank you very much. So I'm going to answer both questions at the same time, they are all related. So normally the feedstock, you have to build one of these chemical plants, you have to secure long-term feedstock coming from potentially the fewer number of sources. So normally the sorting facility that separate the waste produce certain type of qualities of plastic waste. And then we normally apply some type of pre-treatment, which is a conventional mechanical recycling process to separate using optical sorters the PET that we do not want to process, or other type of materials that we believe are contaminants that could have an impact in the yield or in the quality of the tag oil that we are going to produce. Obviously, that has to be, the economics are very important. And if you will do too much preparation of the feedstock, it will be too expensive, and then the process will not work. So it's always a balance of securing the right material from the different marks, from the different sorting facilities that can provide a decent quality, and then to apply an additional step with limited cost to be able to remove the contaminants that we don't want to process ideally. Obviously, that is not possible to remove all of them totally. So you have to assume that you are going to be processing contaminants with up to something like about 20% in order to be able to make the process economically balanced.
Okay, thank you very much, Carlos. It's time to move on to our next finalist. Next up, please welcome from Sunwind Solutions Malaysia, you are Unithan.
Hello, can you hear me?
Yes, we can.
Just let my camera. Yeah, good day to everyone. Thank you very much to all the organizers for inviting Sunwind. As a Malaysia Award winner, we are happy to be present at the finals. I'd like to now share my screen. Sorry, are you able to see it?
Yes, we can. Yes.
All right. So the process that we have developed, I hear all the presentations.
We are on your, we aren't seeing the first slide. We need to go back to the slide presentation. Yeah, that should do it.
Can you now see it clearly?
Yes, we can. Yes. Thank you.
Yeah. So our technology is a patented process that mitigates the formation of two contaminants in refined palm oil, which is 3-MCPDE and GE, 3-monochloropropane diol esters and glycidyl esters, which have been found to be harmful to human health with some carcinogenic properties. So our technology, the screen isn't moving, sorry about that. Yeah, I hope you can see that. So this is a real big problem for the edible oil industry in general, and particularly for palm oil, because the levels of 3-MCPD and GE in refined palm oil are high, and therefore cannot be used by the food industry. As you know, more than 80% of the palm oil produced all over the world is used in the food industry. And so when we looked at solving this problem as a practitioner in the industry, I looked at all the issues that people in the industry might face, and which is related to the fact that in trying to solve this problem, are we going to lose throughput? Are we going to increase cost? Are we going to have an environmental problem? because 3-MCPDE is formed because of the presence of chlorine as a contaminant, and you need to remove it. Therefore, any washing systems that people have put into practice creates effluent treatment problems. And if no solution that is practical and cost effective is found, it means that palm oil cannot be used for edible consumption. And likewise, many other edible oils also would face a similar problem, which would become a global problem because oils and fats are an essential part of what we need to produce and consume. So our technology involves three parts. I think in the interest of time, as the slide is not moving, if I could just show you a short video of the entire process. I hope it's coming up on screen right now. Are you able to see that?
Yes, we are.
Vegetable and palm oil refineries face common challenges. EFSA contaminant standards of max 2.5 ppm, 3-MCPDE and max 1 ppm of GE for palm oil. A technology that can deliver this along with minimizing oil loss, best efficiency while protecting our environment. SunWind's innovative patented technology achieves all this and more with no chemical additives. Here are the 3 steps that makes this happen. Step 1. Our extraction system will selectively remove chlorine from oil into the water phase with virtually no oil loss. 0.1% max versus 1 to 1.5% loss in centrifugal separator systems uses just 10% of the energy to do it and 5% of the maintenance cost. There is no oil-water emulsification in our process, resulting in almost nil oil, 0.1% max, loss in wastewater, and hence low COD in wastewater, which is easier to treat and more environmentally friendly. Our extraction system is fully automated, integratable, or can be standalone. Step 2. Our patented proprietary adsorbent RedGem reduces precursors to 3-MCPDE and GE, and also has lower oil loss in spent earth. Same or better RBDPO quality, color, and M&I. Step 3. GE post-stripping. Our process strips out GE without using an energy-intensive and complicated vacuum system. Get oil that's 100% better than EFSA standard with minimum oil loss and lowest OPEX with SunWind.
Yeah, can you hear me now?
Yes, we can, yes.
Yeah. So what we have come up with is a very simple modification to the existing edible oil refining technique that edible oil industry players, whether it is palm oil or any other edible oil, can deploy with very low capex and very low opex. In fact, we can meet 3-MCPD and GE standards for refined palm oil with 100% better standards than what EFSA has stipulated for an OPEX cost increase of less than $2 per ton. Now, this is very significant because if such a method was not developed, then the industry would have to pay a huge price in terms of mitigating this problem, and that would have led to non-availability of palm oil for edible consumption. As you know, palm oil goes into so many food products all around the world and is the most productive oil crop, and therefore is also the most cost effective. So I wouldn't go through the rest of my slides, as I believe. Are you still able to see the slides coming up?
No, at the moment we can just see you.
All right. So in summary, what I would like to say is we have developed a process that meets all the requirements of what the industry needs with minimum disruptions to the plant, because we can seamlessly integrate it into a refinery. There is absolutely no drop in plant throughput, which means it doesn't increase their OPEX. At the same time, they get maximum value for the nameplate capacity of the plant. It, of course, meets all of the EFSA standards. It doesn't create effluent treatment problems because There is no oil loss in our proprietary liquid extraction system. We use no additives, which again protects all of the certification that is needed for a food product. And we do all of this with virtually no increase in maintenance cost because our technology does not involve any rotating and moving parts. Everything can be integrated into an existing refining process SCADA system, and we have offered this to the industry. And now that the European Union has come up with the latest EFSA standards, which go into effect from January 2021, that all edible oils must comply to the levels of 3-MCPD and GE as stipulated. We are now offering this patented technology to the whole world, and all of the edible oils can now use it as a very cost-effective solution. Thank you very much. I would be happy to take any questions if you have.
Okay, thank you very much. So once again, we pause for Q&A. So if you have a question, please type it in now. We have our first question. How low can your technology achieve in ppm of 3-MCPE in the palm oil?
Very good question. The EFSA stipulates for palm oil 2.5 ppm for 3-MCPD and 1 ppm for GE. Our technology guarantees half of that, less than 1.25 ppm 3-MCPD and less than 0.5 ppm of GE, and at a cost increase of less than $2 per ton.
Okay, thank you very much. That is all. So we will move on to our next finalist. Thank you very much for your presentation. And next up, representing the joint entry from UCL and Heathrow Airport, please welcome Massimiliano Materazzi.
Hello, can you see the screen?
Yes, we can see you and we can see the screen.
Fantastic, thank you, Matt. So my name is Massimiliano Materazzi. I'm a research fellow of the Royal Academy of Engineering at UCL. And in the next 5-10 minutes, I'll give you a little bit of an overview of this project that regards advanced recycling solutions for waste plastics in airports. So before that, just to give you an overview of how bad the situation is, we know that 2.5 billion of metric tons of solid waste are produced around the world, and of these, approximately 275 million tons is made of plastic waste. Airlines and aviation sector in general, which is already known to be a big polluter in the sector, also does his bits in producing these plastics. So airline passengers alone generate approximately 6 million tons of waste, most of which goes to landfill or incineration. Now, the pandemic this year has even worsened the situation, because if it's true that we have less commercial flights going around the world, it is also true that we have a new wave of plastic waste generation due to disposable of masks and gloves. So definitely this is a problem which it needs to be tackled as soon as possible. Regarding the project itself, airports can do something to kind of minimize this waste generation, and where possible that should extract value from the remaining waste, aiming at sending zero plastics to landfill. You might be familiar with the waste hierarchy approach, whereby obviously prevention, reduction, and recycling are by far the most sustainable solutions when dealing with plastics, and with the least preferred options being energy recovery, like in incineration or landfill. Now, Heathrow Airport, which is one of the biggest, is the biggest airport in the UK and one of the biggest in Europe, does produce approximately 26,000 tons of waste per year, and only a fraction of this, 40%, is currently recycled. The vast majority of what's remaining is either sent to an energy from waste facilities in lakeside, incineration basically, or landfill. And that's where the challenge lies, because obviously it's difficult to recycle all the plastics available, and mostly due to the presence of contaminants and like food or other no easy to recyclable waste types. So in all of these, there is a new brand of research, which is a chemical recycling. We heard some presentation before, which basically sits on top of energy recovery together with other conventional recycling techniques. And this would basically allow to divert these recyclable fraction from waste and landfills and convert into, let's say, its original oil state that can be then furtherly reformed to produce new materials or even new fuels. And this would be absolutely in line with the circular economy approach. The benefits of this, as I'll show you shortly, would be reducing greenhouse gas emissions, increase overall recycling rates, reduce plastics leaks into the environment, displace fossil consumption, and above all, also a new opportunity, which is that of possibility of integrating this technology with the hydrogen economy, and I'll show you in a bit why it is so. So in 2019, Heathrow Airport and UCL have partnered up to basically do this pilot project whereby waste from aircraft from Heathrow Airport and along with the terminal waste were treated in a pilot unit that we had in our labs in chemical engineering at UCL, and that was then converted into oil that together with the use of renewable hydrogen coming from water electrolysis could be upgraded into green chemicals, recycled materials, so the plastic to plastics loop, or even advanced fuels. And these can be particular advantages for those sectors which are currently very difficult to be decarbonized, like for example aviation. Now, these obviously does not classify as a recycling, but could be a nice interim options to provide alternative fuels, provided that you have substantial carbon benefits. And that was also part of the objectives to prove that that can be possible. The process is basically a two-step process, whereby the plastics is firstly go through a first stage of catalytic depolymerization, whereby polymers are broken down into smaller one, and the products are then cleaned and refined into a second stage, a product upgrading, where we basically have a clean, high quality oil as a product that, as I said, depending on the operating conditions, can either be used for selective jet fuel production or for making new plastics. Another important feature of the process is that it's able to make use of intermittent renewable energy when this is available, because that can power, for example, a water electrolyzer to produce green hydrogen, which takes part into the reactions, but also some more hydrogen is produced by the reaction itself, so leading to a product which is a mix of green and blue hydrogen that ties up very nicely with the current new developing infrastructure for low carbon hydrogen distribution. The project went through several milestones. So in summer 2019, we start collecting waste batches from Heathrow, from Terminal 3 and 5, from their mechanical recycling facilities. So taking all the plastics that was not recycled by their conventional mechanical facilities, and also some general waste to see what we could do with that. And this was tested extensively in our units at UCL. And then we did an extensive product analysis to see what chemical compositions of this for the gas products, for the liquid products, and therefore develop a model for the full scale commercial facilities. The final step was to assess the environmental benefits of these processes, and we looked at the full life cycle analysis of the process, including the cradle to cradle if you want to go to plastics, or the well to wheel in case you want to look at the substitute fuel production. And so we could compare the two routes with the current alternatives, namely fossil fuels or incineration or plastics production. And the results were quite interesting per se. You can see that waste plastics, when it is used to produce, for example, jet fuel, the carbon footprint of such fuel is not too dissimilar from some other, let's say, biofuels. So this was quite an interesting outcome of the project. And also the benefits are much higher when we compare the technology with what is the current destined for recycled plastics, which is incineration. And you can see that the carbon footprint was significantly lower compared to incineration. We also compared the technology in case you want to go for the closed loop cycle plastics to plastics with what is done now with the plastics. And obviously you can see that, as you can imagine, the carbon benefit are much higher, and with a net carbon contribution close to zero. So if we take into account what's the avoided carbon costs of that plastics as the current disposal routes are. So the project outcomes of this nice project were multiples. It was a very good technical learning for the team, especially for validate the technical approach of using a catalyst in the depolymerization reactors, or the use of renewable hydrogen to increase the yields of products. It had a very good educational outlook because we involved many students, MSc students from the Department of Chemical Engineering working on firsthand on this project. So to have a very good exposure to this industrial collaboration, nice environmental learnings, and most importantly, this industrial partnership, which is moving on and trying to move to the next phase, which would be the construction of a larger plant at airport to try to make some good use of the plastics that they produce. I conclude just thanking up my team. It wasn't all this work wasn't possible without them, and I welcome any questions you may have. Thank you.
Okay, thank you very much. So once again, we pause for Q&A. If you have a question, please type it into the questions box. While we give you a moment on that, if you've been suitably inspired by what you've seen today and would like to submit your own entry to next year's IChemE Global Awards, keep an eye on our website for entry information. We typically open at the start of March each year. You can find out more at icheme.org/global awards. Okay, we don't appear to have any questions, so thank you very much. We're now going to move on to our final presentation from Impact Recycling. It's James Finlayson.
Hi there, my name is James Finlayson. I'm the Technical Director here at Impact Recycling. My first project was taking the BOSS technology from a lab scale to the commercial scale that you see today, where we recycle over 6,000 tons of previously landfilled or incinerated waste plastics. So BOSS technology, that stands for Baffled Oscillation Separation System. It's a very simple technology whereby a stack of plates oscillates up and down. This creates vortices in the water, and this allows us to separate two floating components. We put this to work on polypropylene and polyethylene, the two most abundant commodity plastics. So this is really our feedstock. It's the pile that's left behind after the easy to recycle plastics have been removed. This pile was previously landfilled, exported, or incinerated. our technology and our process, we don't try and compete for existing recycling feedstocks. We try to add new capacity. And this is why we've really turned our technology to this problem stream. What we're able to do by separating this stream into the high purity outputs of polypropylene and polyethylene, combining it with our additive, is produce high-end consumer-facing products. For example, like this bottle on the left-hand side, this is our HDPE. And these polypropylene consumer goods items, they're for coffee machines, we're able to produce them as well. And with our additive, we can do this and recolor the surface of the plastic. So what is BOSS? BOSS really is a scalable, automated, water-based solution. Traditional sorting technologies that can achieve the same purity as BOSS typically use opticals or electrostatic or similar separation technologies, but this has a limitation in that if you cannot scan it or the electrostatics aren't favorable, you cannot separate it. Our system works using only water, which means that we can separate all polymers based upon their apparent density, irrespective of their cleanliness, irrespective of their color. The way this works in practice is as the stack oscillates up and down, it generates flow lines between the baffles, and these flow lines are generated by vortices. So as the stack oscillates up and down, you have vortex shedding, and the vortices affect the polypropylene in a different way to the polyethylene. It has the effect of increasing the residence time for particles of polypropylene and allowing us to wash out polyethylene particles. And it does this because the separation happens because of the difference in density, or which is ultimately driving the buoyancy of the particle, but also in the drag profile of the suspended particles. And the oscillation in the water combined with our flow rates greatly amplify these differences in both positive and negative buoyant forces. So polypropylene has a density of 0.925 grams per centimeter cubed, whereas the polyethylene that we're recovering has a density of 0.935. So that's a density delta of 0.01 that we're separating on. So this is where BOSS is sitting at the moment in the supply chain. So we have mixed post-consumer plastic, including black plastic, and this is coming from household recovery centres, so places you take your plastics and dispose of them. It's a big commingled pile. What happens then is the waste management companies either take that and they blend it with their MRF output, which is the mixed recyclable facility output, which is where your black bag waste goes. And they take out the choice plastics, really the easy to recycle plastics. The residual fraction then comes to impact recycling. We put it through our shred and wash process to first prepare the material for the BOSS technology, then putting it into BOSS to recover in excess of 98% pure post-consumer PP and PE resins. The yield that we get is about 70%. And what we have coming in is a gate fee item, which we typically take in for free. And we end up with a regrind, which we sell back into UK manufacturing for values in excess of £500 per tonne. Our customers are a range of, so we feed brands, including the likes of Unilever. We also are the front end to any chemical recycling technology solutions. So an example is PCT, Pure Cycle Technologies. We have signed an exclusive license agreement with them over in America to supply our BOSS technologies as the front end of each of their chemical recycling processes. And we also sell direct to compounding manufacturers. So this is a look under the hood of the BOSS system. So you have to imagine you have a column of these baffles stacked vertically, and as these baffles oscillate, this is where the vortices will form. It's very, very simple. We have one moving part to generate all this separation. And the way I think of it is like having thousands of centrifuges between each of these stages, trapping the polypropylene or the lighter component and allowing you with the right settings to wash out another component. That's just another picture there. And then just highlighting again that for the rigid plastics, we are able to separate particles with a density delta of 0.01 grams per centimeter cube. So it's an incredibly compact system. This stack here that you're looking at was a Mark II stack that we had 2 years ago, and this stack was able to deliver 6,000 tons per year on a single shift of recycling capacity. So extremely simple, very passive design. There's only one moving part, which is the eccentric camshaft that drives this up and down. So when we developed BOSS, it was originally developed to look at the problem stream of caps and bottle caps from PET recycling plants. For PET recycling, bottles are individually selected, removed from the pile that you see in the bottom left of the screen there, and then they're sent to be granulated, washed, and the PET is recovered. But you end up with the bottle caps and ring enclosure as a problem stream. The stream is a mix of PE, PP, and residual PET, and that's what we designed our BOSS for. But when we got it working, and we're able to separate to pure polypropylene, pure polyethylene, and pure PET, we realized that the technology could really do a whole lot more than just plug into a single source mechanical recycling supply chain. So we looked at the supply and what was going to incineration and landfill, and of course this is now what we do in Newcastle. By making this stream worth something, we are paying for this material, or we take it in for zero, when in fact it has a negative trading value. By taking this in, we prevent it from being exported to countries with poorer waste regulations, and ultimately prevent it going into the ocean. But to do this, we actually did need to develop some upstream IP. So we developed a unique shred wash pre-purification system to feed our proprietary patented BOSS system. So material comes in, is shredded. So our material comes in, it comes in as you would put it in your bin. We shred it down to 50 millimeters, remove the metal. We put that into intermediate storage because the shredder is obviously a very lumpy output. From there, we wash the plastic, we put it into a density separation tank. We're able to recover two sinking fractions there, one which is ABS and high impact polystyrene rich, the other that is PVC rich. And this allows us to further recycle our non-target plastic components that exist in our feedstock. We put it through a very mild caustic wash before feeding it into our patented BOSS system, which we're looking at here. One BOSS has been optimized for delivering pure polypropylene, the other for pure polyethylene. And what is unique about our system, unlike other active separation systems whereby you're scanning or trying to select the correct component for purification, our system does two things. First of all, the material is driven into the center of the stack to oscillate, and this drives the separation between PP and PE up to 98%. But what we can stand over and guarantee is that the 2% that is contaminating the polypropylene is in fact only polyethylene. All non-polyolefins have been removed. And this is vital for chemical recyclers where their catalysts can be poisoned by non-polyolefins. And it's also vital for mechanical recyclers where their investment in compounding systems can be undermined where PVC or a similar problem, heavy plastics, contaminate the stream. So this is what we produce at Newcastle. It's a clean regrind. This is actually suitable for going direct into manufacturing, and indeed our polypropylene we sell to a well-known paint pot supplier in the UK, and we are one of the 2 suppliers of a grade that is pure enough to produce direct to paint pots, the sort of light grade paint pots you might see in your local department store. So this is really important for sustainability in that we've applied our BOSS technology to a problem feedstock that was previously being incinerated or landfilled. And it was great because we could unlock this very high purity regrind, sell it direct into manufacturing, skip out the entire step of compounding and realize the carbon savings that way. But it turned out that that wasn't really enough on its own. This pile of plastic, as you see it here, is a mix of polypropylene, polyethylene, styrenes, all sorts of other plastics. But also, if you were to separate all the pure polyethylenes, you'd have a wide range of polyethylenes there themselves. You'd have a range of molecular weights, you'd have a range of rheologies, you have pipe grades, you have injection grades, you have extrusion blow molding grades. And it turns out that all of these grades, surprisingly, process very, very differently. And when you mix them all together, you end up with something that is a bit better than some, a bit worse than others, but in terms of processability, slap bang in the middle with no machine really suitable for processing it. big part of what we then did to shore up our business model was look at ways that we could control the rheology. So I'll just play this whilst I talk over. Our material is a mix of molecular weights. Each strand you see there should actually flow at its own rate. So you should see some strands being much thicker than the other, some being quite thin and snapping. And this is a real challenge because the plastic industry itself is set up to accept grades based upon a number of process stability metrics, including the rheology and the ability to recolor. So for example, if we want to sell our polyethylene into an injection grade application, our rheology was too stiff. Our material was simply too stiff to inject it at the rate that they required. Likewise, if they wanted to blow a bottle out of our recycled grade, it was too runny. It wasn't stiff enough. So what we did at Impact is develop a FDA-approved rheologically dynamic additive, which we borrowed from the food processing industry, for use with post-consumer plastics. It essentially uses the same recycled PE as a polymer carrier, which allows us to sell a 100% recycled grade once compounding. And the additive works without changing the latent mechanical properties of the plastic. So we spent all that time trying to mechanically sort and purify polypropylene polyethylene. And this allows us to preserve, because there's no thermal history there, the mechanical properties of the plastic. By combining it with the additive, we can then control the melt flow rate, control the rheology, to the point where we're able to make perfect extrusion blow molded bottles. So what you're looking at here is our plastic 100% PCR being extruded through an extrusion blow molding line. Normally what you would see with a mixed source feedstock like ours is these tubes descending at different rates or collapsing. But the additive, through the way it works, allows us, under these temperature and pressure conditions, to flow the material at exactly the same rate, at exactly the rate that we tell it to flow at. And this is quite unique in that typical melt flow control solutions have involved chemically altering the bonds inside the plastic, whereas we describe our additive as a rheologically dynamic additive. It's actually completely passive unless it's under certain shear and temperature conditions. The way the additive works, by occupying the boundary layer between the extrusion equipment and the melt phase, allows us to actually recolor the surface of the polymer. We can select the thickness of that boundary layer, and by adding master batch with an affinity to the additive that's held within the carrier, allows us to recolor the polymer. So that black polymer you saw before was our rheologically controlled polyethylene. This is our polyethylene with master batch added on top. Now these colors appear very bright, and that is what it's like when it comes out hot. And as the polymer cools, the color does become a bit more pastely. A bit more pastely, like what you can see on the left-hand side here. And so why do you want to make a bottle, I suppose, out of post-consumer feedstock like that and avoid the energy associated with chemical recycling? Well, it's quite simple. The mechanical properties have been preserved throughout the lifetime of the plastic product. So here we did an example between a virgin bottle and our PCR bottle. The virgin bottle had a top load capacity of 28 kilograms. Our PCR material had a top load capacity of 22 kilograms. The standard for this particular bottle is 9 kilograms. So there's plenty of life left in this plastic. And why is this all important? Well, I think it's really useful to look at the plastic pact when trying to evaluate what technologies we need to actually address the plastic problem and how quickly we need to develop them. The top left one here, by 2025, 100% of plastic packaging to be reusable, recyclable, or compostable. Well, by bringing BOSS to market, we've changed what is considered recyclable. That pile that was previously being incinerated or landfilled, local waste operators, local to us in Newcastle, are now actively seeking that material as opposed to trying to get rid of it or seeing it as a problem. It's very much a case of build it and they will come. When we first went to Newcastle, people said that material didn't exist, but that didn't make sense to me because I could see it in the shops and we were throwing it in our bins. After 3 years of being at Newcastle, we now unfortunately don't have the capacity to accept all the deliveries that we can take in the local area. By So the next one, by 2025, 70% of plastic packaging effectively recycled or composted. Well, this is about having the infrastructure there by 2025. We have our plant there in Newcastle now, which shows that we are addressing this problem and opens doors to brands and hopefully broadens our sales channels. But over the next 2 years, we have plans to open in the Northwest at 25,000 tonnes per year and in Groningen in Holland at 25,000 tonnes per year. And all of this for an investment less than 10 million euros. It's completely different to the proposition of chemical recycling in that the economics allow this to work at the local level. The OPEX is favorable enough, as well as the CAPEX. And the last one, by 2025, 30% average recycled content across all plastic packaging. This is only going to be achieved if you can separate that big problem pile into very high purity single source plastics, but then also marry those single source plastics up to specific outputs as we do with our additive. But when we consider sustainability in the round, it's not just the littering problem that we're addressing, it is actually the carbon savings that are the real winner. Every ton of mechanically recycled polymer displaces 1 ton of virgin polymer, as well as the emissions associated with incineration and export. So when we consider that we're displacing a ton of virgin and also preventing incineration, the maximum CO2 savings, or the maximum CO2 cost, sorry, of chemical recycling, or indeed the one being proposed by BASF in the paper that they shared around, was 4.2 tons of CO2 per ton of recycled polymer produced. When you look at incineration, if you were just to incinerate and then replace that virgin, it's 4.51. Mechanical recycling, according to Deloitte in 2015, including all transport and infrastructure emissions, came to 0.35, whereas our Boss mechanical recycling, by virtue of its very simple design, very low energy requirements, and very, very high throughput relative to its floor space requirement, is 0.125 tons per ton of plastic produced. So what's next? We started our Boss project in 2010 when we accidentally stumbled upon the mechanism for separation. We had a patent granted in 2016, and we're on with our expansion into licensing in America, as well as opening plants throughout Europe. In addition to that, we have R&D in the pipeline, and we have our Boss technology now working on flexibles, specifically separating monomaterials, so polyethylene films that are just polyethylene, from multi-material films and laminates. So for example, polyethylene PET polyethylene tie layers or polyethylene aluminium laminates. We've also got Boss working on fishing nets, carpets and clothing fibers, so not just the rigid or the flexibles, but the sort of unidirectional orientated fibers. And this is a massive problem in America where most carpets are actually polypropylene and most of them are incinerated. We have had really good success with medical waste streams. So orange bag waste, for example, in the UK, is waste that the NHS produces. It needs to be sterilized before it's ultimately disposed. And once it's been sterilized, it then goes for incineration. This particular stream is a blend of rigids and flexibles, and over 90% of it is polyolefin. And it just goes straight to incineration. You know, NHS Scotland, that's over 70,000 tons per year going to incineration. We've developed our Boss technology to separate the rigids from the flexibles and into polyolefins, and then plug into our existing recycling infrastructure within impact recycling. We're also looking at getting Boss to work on technical polymers, so separating out HIT ABS from other problem technical streams. And this can be, again, used to either feed chemical recycling facilities or back into mechanical recycling. Thank you for listening.
Okay, thank you very much, James. For the final time today then, if you have a question for one of our finalists, please submit it now. We do have one already. You mentioned a comparison with centrifugal separation. Can you comment further on the benefits of the Boss over the centrifugal option?
It really just comes down to intensification. So if you have a centrifuge and you're separating it and it's this particular size, we've taken that concept really and tried to intensify it as much as possible. I think of our Boss separation technology as a series of stages. Each stage has over 400 individual centrifuges working in an oscillatory fashion. So it's really like unlocking the physics that drive separation in a centrifuge in an exceptionally condensed space and in a very intense manner. So this allows us to greatly increase the throughput, maybe 3 or 4 times that of a centrifuge for the given floor space and water consumption. But I also believe it allows us to, to achieve higher purities because of the multiple stages that you can have. Yes, you can have multi-stage centrifugal separation, but not really the way that we have it. Is very, very condensed, and it's multiple stages with multiple centrifuges.
Okay, thank you. That wraps up our questions. So thank you very much, James. Right then, we have now heard from all of our finalists. So I'd like to thank all of them for joining us today and for telling us more about their work. I'm sure you'll agree it's been a range of very interesting, very different projects. But now it's time to reveal the winner. So let me start with our highly commended entries. And they are Dow Europe and the joint entry from Dow Europe and H&S Anlagen-Technik. So well done to everyone associated with that work. But now I'd like to hand back over to Johnson Matthey's Ashley Anderson to announce the award winner.
Okay, everyone, am I back on screen?
Yes, you are.
Yeah, excellent. What an excellent set of entries into that sustainability category. Really enjoyable couple of hours. So, ladies and gentlemen, it gives me great pleasure to present the winner of the IChemE 2020 Sustainability Award, sponsored by Johnson Matthey, and that is Plastic Energy.
Okay,
so,
well, congratulations.
Congratulations to Carlos and the Plastic Energy team.
Yeah, well
Thank
done,
you very
Carlos.
much, Ashley. Thank you very much. It's very much appreciated, Ashley. Thank you very much for the organization. It's a great honor for us to receive this award. It's going to make all our team extremely happy. Thank you.
Well done.
Excellent.
And thank you, Ashley, and thank you, Johnson Matthey, of course. So well done to all of our finalists, and Plastic Energy, now contender, of course, for our top prize, which we'll be announcing the winner of tomorrow afternoon, the Outstanding Achievement in Chemical and Process Engineering Award. There's still time to register for that webinar if you'd like to join us. It's free to attend and open to all. But for now, that's the end of today's webinar. So thank you very much to everybody for being with us, especially our sponsor and our finalists. But congratulations to Plastic Energy, winner of the IChemE 2020 Sustainability Award.